so good morning to all. It is our great pleasure to welcome Professor Yoshiharu Kohayakawa. Professor Kohayakawa obtained his PhD at the University of Cambridge under the supervision of Leila Golobash, after which he returned to the University of São Paulo in Brazil, where he has been a professor since 1985. Professor Kohayakawa is a member of the Brazilian Academy of Science and has contributed substantially to the advance of extremal combinatorics, probabilistic methods, and random theory. So let's welcome Professor Kohayakawa.
Carlos, thank you very much for the introduction. Thank you very much to you all for coming. So it's already Friday. It's been a wonderful week, very exciting. So I'm very impressed that you are still here. Okay, so thank you for coming. So I will speak about extremal problems for random discrete structures. It's a great honor for me to be one of the speakers of this Mathematical Congress of the Americas. Thank you to the organizers. So the aim of the talk is to report on a certain line of research in probabilistic combinatorics that I've been involved with for some time. And that is, to be more precise, some probabilistic versions of certain extremal results in combinatorics. They are mostly density results. I will kind of use this term during the talk, and I hope that it will be clear what I mean by that. Okay, so the outline of the talk will be like this. So there will be a fairly long section of preliminaries so that you have some idea of the context in which this research is in. So I will define graphs and hypergraphs. I will talk about sets of integers. I will talk then for some time about classical extremal results for graphs, focusing on very simple examples so that those of you who are not familiar with this, I hope will get an idea of what one looks for in this area. Now, I will then talk about degenerate extremal problems because those will be important later in the talk when I talk about more recent results. And also all of this, up to this point, before random graphs, everything will be deterministic. But then I will start talking about random graphs, so that will be the probabilistic component of the lecture. Okay. So I will kind of try to put all of this together, and then I will start talking about these probabilistic versions of extremal results. That will be the main part of the talk. And then I will go on to degenerate extremal problems. I will, in particular, focus on Sidon sets, some problems related to Sidon sets, which is some structures, some objects of interest in additive combinatorics. So I will start with the basics. I will start by saying what a graph is. So a graph is an ordered pair, V, E. So V is the set of vertices, E is the set of edges, and to me, and for us here, an edge is just an unordered pair of vertices. So here's a graph. So it's a nice picture. This just happens to be. This is some graph on 500 points or so, very nicely drawn by this Valdis Krebs. This is the collaboration graph of co-authors of Paul Erdős. Anyway, so this is a graph. I'm pretty sure you are familiar with this. Now, hypergraphs, I won't talk so much about hypergraphs, but let me define them anyway. So a K-uniform hypergraph is again a pair, V, E. So V is the set of vertices. And now the E, the set of, now you have hyperedges instead of edges, and these hyperedges will be unordered K-tuples of vertices. So in the case K equals 2, you just have a graph. In the case of K-uniform hypergraphs, instead of an edge joining 2 points, you have a hyperedge which contains K points. So for instance, these are two hypergraphs. For some reason, they are called F1 and F2. This 3 here on top is there just to express the idea that this is a 3 uniform hypergraph, so the hyperedges have 3 elements. So this is one way of drawing them, but maybe this would be a nicer way of drawing them, but they take up more space. Anyway, so these are 3 uniform hypergraphs. Now, sets of integers, okay. So we'll be talking a lot about the first n integers. So this is a representation of the first, an initial segment of the integers. And we'll be interested in subsets of it. So maybe such a set A, right? So marked here in red. And you can ask interesting questions about even such a simple thing. So for instance, you can ask whether this contains an arithmetic progression on some number of elements. Let's say in my picture, 4 elements. And the answer in this case is yes. This set A does contain 4 elements forming an arithmetic progression, a 4-term arithmetic progression. So there are equally 4 points that are equally spaced. Okay. Now we move on to classical extremal graph theory, and I'll use one of the, probably this is really the first result, it's considered to be the first result in this area. This is Mantel's theorem. Okay, so in Mantel's theorem, let me first read. So any graph G on n vertices with more than n over 2 times n over 2, round up, round below, round up, round down, round down, round up. If you have more than that many edges, then you must contain a triangle. A triangle is just 3 mutually adjacent points. My notation for that is K3. Okay, so what does this theorem say? Okay, so if you have n vertices, and if you split these n vertices into n over 2 and n over 2, well, if n is odd, then you round up here, round down here, let's say. And if you put all the edges across, you don't contain a triangle. You will not find 3 mutually adjacent points because 2 of them will be on one side, and I didn't put the edges inside the block. I only put the edges across. Okay, so it's very easy to see that there is a graph on n vertices and this many edges which does not contain a triangle. And the theorem says that if you have one more edge than this, then you must contain 3 mutually adjacent points. Okay. So this is Mantel's theorem from 1907. Let me introduce a piece of notation. Let me introduce this x function, this sometimes called Turan function or this extremal function. This is defined, so this is defined as follows. So you have some forbidden graph f. So in this case, we are talking about triangles. So this graph f would be K3. And then you're interested, there is some parameter n here, and then this shows up here in this definition. Kn is the complete graph on n points. So you have n points and choose 2 edges, all the possible edges. So you're interested in this definition in the following. You look at graphs that are contained in this Kn, so graphs on n points, that's the same thing. And you are interested in knowing what is the maximum number of edges such a graph G can have if this forbidden graph F is not a subgraph of G. Okay, so again, X and F, I repeat because this is really the basic, most important definition in the lecture. So X and F means if I have n vertices and if I do not want to have a copy of F, how many edges can I have in my graph G? And the answer is X and F, right? And so, for instance, Mantel's theorem tells us that this xn of K3 of the triangle is this quantity here. Right? It gives a precise answer for the question, how much is this extremal function for the triangle? Okay, now, very soon I will not be I cannot say so much about such precise results. It will be more convenient to talk about the density threshold. What do I mean by that? So, for instance, Mantel's theorem says that half is a density threshold for triangles. That means the following. If I have a graph G, and if the density of G is a little bit more than 1/2, so half plus epsilon, then G must contain a triangle. What is the density of the graph is naturally defined, right? So you count the number of edges you have in the graph and divide by the total possible. Total possible would be n choose 2. And this number, n squared over 4, roughly n squared over 4, is half of this total. And this weak form, this density statement, is that if you have slightly more than half, then you must have a triangle. So it's a weak form of Mantel's theorem. So if you like, so half is the same so this half here is the same as half here that appears in the expression of x in K3 if you write it in this form as a constant times n choose 2. So in other words, so let me say it again. So if you think of this, you have n vertices, you could think you have the empty graph here, you have the complete graph here on the top, and here you have a Boolean algebra, right, of all the subset, of all the subgraphs of the complete graph, right, empty and the complete. And as you go up, you of course become more likely to have 3 mutually adjacent points, a triangle. And the question, this x is, so how far can you go if you avoid triangles? And this density threshold kind of says that if you go up, and if you hit the middle, then if you go a little bit above, then you are dead, you must contain a triangle. So that is what I mean by this density threshold. Okay, so I hope, so we went very slowly over this slide because this is a crucial concept. But now, still, in talking about history of extremal graph theory, let me talk about another isolated result. This is actually a result that Paul Erdős proved in 1938. So he was interested in the following problem. What is the maximal cardinality of a multiplicative Sidon set S? If this set S is contained, is restricted to be in the numbers 1 up to n. What is a multiplicative Sidon set? There is the usual Sidon set, this is the multiplicative version of it, and the definition is this thing here. So you say that a set S is a multiplicative Sidon set if you take all pairwise products, if they're all different. In other words, so some other different way of saying it is if 2 products of members of your set are equal, then actually you have the same set, right? So all the pairwise products have to be different. This is a multiplicative Sidon set. So a multiplicative Sidon set containing brackets n, the first n integers, is the set of primes. If you take, right? It's the set of primes. So if you ask how big such a set can be, then it can be at least as large as pi of n, the number of primes that you have in 1 to n. And the theorem of Erdős is that this maximum is actually only just a little bit bigger than pi of n. So pi of n is n over log n, and you just have this little extra term here n to the 3/4. And now, so his argument is based on a graph theoretical result. So his key tool is a result on the extremal, is a solution to an extremal problem for graphs. So here's the bit of the paper in which he says this. So he says, the argument was really based upon the following theorem for graphs. If you have let 2k points be given, we split them into 2 classes each containing k of them, so k and k. Now the points of the 2 classes are connected by segments, so those are the edges of his graph, such that the segments form no closed quadrilateral, so you don't kind of have this, right? So he had just proved at this point that the number of segments, or the number of edges in this graph is at most 3 times k to the 3 halves. It's a bit hard to read, but that's what it is. So k to the 3 halves. Okay, so this was some instance of an extremal problem for graphs that Erdős solved to solve a problem in number theory. Okay, now so those are considered to be 2 kind of isolated results in the theory. And the area of extremal graph theory is considered to have been born with Turan's theorem. Turan's theorem is like this. So Mantel was about triangles. Erdős talked about a 4-cycle, a quadrilateral, closed quadrilateral as he called. And Turan said, well, okay, what is this extremal function xn for complete graphs, for general complete graphs? I want to know how many edges or what density forces a graph to contain q plus 1 mutually adjacent points, k, q plus 1. Okay, so I'm saying here again that this generalizes Mantel, so Mantel was the q equals 2 case. Okay, so in Mantel's case we said, well, if you want to avoid triangles, you take the vertex set, split into 2, put all the edges this way, you have no triangle and you have lots of edges, and that is the best you can do, right? And for Turan, you do something very similar. So this graph TQN is the following. You take your vertex set, you have n vertices. The parameter q is this q here. You split this, your vertex set, into q parts and put all the edges across. You don't put any edges inside any class, right? Okay, it's very easy to see that if you do this, well, the best thing you can do if you want to maximize the number of edges is that you make all the q parts as equal as possible, and that maximizes the number of edges across, so joining different classes. It's very easy to see that this graph does not contain q plus 1 mutually adjacent points, because if you pigeonhole, q plus 1, 2 will go into the same class, and we didn't put any edge in any class. Okay, so this gives a lower bound for this extremal function, for this Turan function, for the complete graph on q plus 1 points, and the Turan's theorem is that this is the best you can do. That's precisely the maximum you can achieve. Okay, so Turan solved this problem, determined this function for complete graphs, and actually, in the language of density, the density threshold for this complete graph on q plus 1 points is 1 minus 1 over q. So for q equals 2, it was half, right? So it's 1 minus 1 half, so it's consistent. Right, and it's this because if you count how many edges you have in this Turan graph, TQN, you get 1 minus 1 over q, asymptotically 1 minus 1 over q times n choose 2. So that's the threshold for q plus 1 mutually adjacent points. Again, if you are in the Boolean algebra here of the empty graph, full graph, as you go up, when you hit this point above it, you have no chance. You must contain q plus 1 adjacent points. That's Turan's theorem. Okay, so we started with triangles in 1907, then Turan in 41. And now you can ask about general graphs, of course. And there is a very neat answer for this. So let f be an arbitrary graph, at least one edge, to avoid trivialities. So let's just mimic the lower bound that we have been discussing. So the lower bound for this extremal function is related to the chromatic number of this graph f. So I define this chromatic number here in this way. It's the smallest q such that f it can be embedded in this TQ very large number of vertices. So you may know this chromatic number as the smallest number of colors that you need to color the vertices of this graph F, so that every edge gets the endpoints, at the endpoints 2 different colors. This is the same thing. Anyway, so it's the smallest q such that you can embed F into this TQ very large number of vertices. And if you just repeat what we've been doing about splitting n vertices into 2 parts or q parts and so on, in this case you split into this number minus 1 because you see f couldn't be embedded here, so you just take 1 less. Then of course this is a lower bound for this quantity, and this happens to be, well, okay, this number, the number of edges of this graph is this. And this is the famous theorem of Erdős-Stone and Szymonovitch. So Erdős and Stone proved the main, so this is known as the Erdős-Stone-Szymonovitch theorem. For any graph f, at least asymptotically, you know that this function is this. Is this quantity times n choose 2. Or if you like, the density threshold for this graph f is tied with the chromatic number of f, and it is 1 minus 1 over chromatic number of f minus 1. Okay, so this is a very good answer, very neat, very clean answer to the question of what is the density threshold for an arbitrary graph f. Okay, now let me talk about something that, so this is a very good complete answer, let's say. But then if you notice the following, so if the density threshold of f is this quantity, if the chromatic number of f is 2, so if this quantity is 2, you get 1 minus 1 over 2 minus 1. So 1 minus 1 over 1, so you get 0. So this density threshold is 0. Right? What does that mean? That means that this extremal function that we are interested in is little o of n squared. That's definitely information. So that means that if you have a graph on n vertices, and let's say 0.1 times n squared or 0.0001 times n squared edges, then you must contain a copy of this graph F as long as n is large enough. There's definitely information, but maybe you want more information. So for instance, this is again this piece of Erdős's paper. And so he was interested in the extremal function for this closed quadrilateral, right? So we call that C4 or full cycle in modern terms, let's say. And what he essentially proves here is that this extremal function for C4 is at most is big O of n to the 3 halves. And that's really crucial. So to have such a good bound for this function is crucial for him to prove what he wanted to prove. He was interested in proving the maximal size of a multiplicative Sidon set contained in brackets n. And he wanted to get this error term n to the 3/4. So he was interested in a small error term here, right? So it was very important for him that he could get a good bound for this extremal function. So knowing that it's only little o n squared is not always enough. Or, yeah, you want to know, right? What the answer is. Okay, so degenerate extremal problems. So those are the ones in which the density threshold is 0. Or if you like, this extremal function is little o n squared in the case of graphs. So that is what I mean by a degenerate problem. So in this case, it's natural to try and prove more. So it's natural to try and prove that this extremal function is actually n to the alpha for some number alpha which is strictly less than 2. That is the natural thing to try, right? And in fact, this seems to be a very difficult problem. So for very basic graphs F, one cannot do this. One has not been able to do this. So for instance, if you talk about a long cycle, long even cycle, so you don't really know. There are conjectured values for this alpha, but it's not known. There are amazing conjectures about this. So for instance, it's conjectured that if you have some F here, a bipartite graph F, chromatic number 2, a degenerate case, then this function is asymptotic to some constant, some real constant C positive, times n to the alpha for some rational alpha. So it's conjectured that this alpha here can only be rational. It's also conjectured the inverse way. So if for any rational between 1 and 2, it's conjectured that you can find some graph F for which this is asymptotic to n to the alpha, at least up to constant in this case. Yes. Yeah, okay, not even that is known. Even for complete bipartite, it is not known. So there are some cases that's known as the Zanekiewicz problem. Yeah. Okay. So in the degenerate case, you're really interested in proving something like that. But even proving that some extremal problem is a degenerate problem, namely that the density threshold is 0, can be really very hard. So let me show you an example. Not the case of graphs, because in the case of graphs, coincides with the case in which the chromatic number F is 2. But you can move on to different structures, such as hypergraphs or integers, and then you kind of get very difficult problems. So here's one such problem. So this is a paper of Erdős and Turan, which became very famous. This is a paper from 36. So it's called On Sequences of Integers. Yes. So let me read. So consider a sequence of integers, a1, a2, up to big N, containing no 3 terms for which ai minus al equals minus as, maybe. In other words, it does not, so this set, the sequence a1, a2, and so on, the sequence does not contain 3 consecutive terms of an arithmetic progression. It doesn't contain an AP3, 3-term arithmetic progression. And then they define this R to be the maximal size of maximal length of such a sequence, given N. And their aim is to estimate this function. So here is theorem 2. They prove that this quantity is roughly, it's at most 4/9 times N, with some little epsilon. So 4/9. So they're able to show that for this extremal problem, the density threshold is not bigger than 4/9. Then actually they work a little bit harder. They analyze some smaller cases. They do some work, and then they can improve it to 3/8. And then they say at present this is the best result for Rn. And then they conjecture, so they say it's probable that this Rn is little o n. So this is now a very famous problem. So this is the Erdős-Turan conjecture on arithmetic progressions, which has a very interesting history, and it was finally solved by Semmelredi. So let me now state Semmelredi's theorem. So let's define the extremal function this way, Rk of n, this is the standard notation. You look at the initial segment of the integers, brackets n, you're interested in sets that do not contain a k-term arithmetic progression. How big can such a set S be? So my notation here, APK is k-term arithmetic progression, and brackets n is first n integers, right? So how big can this function be? So in the Erdős-Turan paper that we just looked at, k was 3, so this is a general case. And Semmelredi's famous theorem is that for any k, so you can not only 3, but for any k, for any epsilon, if n is large enough, this extremal function is at most epsilon times n. Or if you like, this extremal function is little o n. Or if you like, the density threshold for this problem is 0. Maybe if I were to follow the previous notation, maybe would be this, right? In this notation, I put here in the second argument the object that I forbid, right? And we're forbidding k-term arithmetic progressions. Okay, so as we just said, Semmelredi's theorem is precisely the statement that the density threshold for this problem is 0. So as I said, proving that the density threshold is 0, that a problem is degenerate, can be very difficult. This is a very famous theorem with a very interesting history. So this inspired a great deal of further exciting work. So the natural thing to do now would be to speak what came next, which is very interesting, very exciting, very different proof by Furstenberg using ergodic theory of this theorem. However, if you're interested in such ergodic theoretic things, you are probably not here. You're probably in this, listening to Alejandro Mas, who is speaking exactly the same time now. So let me just read the beginning of his abstract. So he says, the connection between ergodic theory and additive combinatorics started in the 70s with Furstenberg's beautiful proof of Semmelredi's theorem via ergodic theory. So this is not the direction we go into. There is one direction we could go into, and that is the relation between extremal hypergraph theory and arithmetic progressions and Semmelredi's theorem. I will just say just a few words about it. So Frankel and Rödel proved that there is a certain particular extremal problem for hypergraphs. So it's a problem about estimating this x function. But now I have to put here two hypergraphs. So they proved that proving that this function is at most little of k minus 1 implies Semmelredi's theorem. So you can actually derive Semmelredi's theorem from a purely extremal problem for hypergraphs. Actually, for k equals 3, the hypergraphs f1 and f2 that we had at the beginning are precisely those. But it doesn't so much matter. I will not say much about this. So in other words, proving this estimate for this extremal function contains Semmelredi's theorem. So it's expected to be difficult. And in fact, this has been proved generalizing the method of the regularity method of Semmelredi, generalizing the regularity lemma for graphs due to Semmelredi to k-uniform hypergraphs. So this also has an interesting history. So for k equals 4, this was done by Frankel and Rödel, and then two different groups of people achieved this project of proving Semmelredi's theorem via this hypergraphic extremal problem independently and at the same time. One group was led by Rödl and with his co-authors Nagel, Schacht, and Skokan, and the other group, Singleton, was Tim Gauss. Now this led to still further interesting work by Terry Tao and Elek and Szegedi. But then again, this is a direction we do not go into. We go now to random graphs. Okay, we're still talking about preliminary, so far everything was deterministic. Now we talk about probabilistic combinatorics. We talk about random graphs. So Erdős and Rényi, around 1960, wrote a few papers. There are two that are major papers, in which they started some systematic study of random graphs. So their models are these GNM and GNP. So let me define them. So n, again, is the number of vertices that you have in your graph. And in this model, GNM, you do the following. So you have n vertices, and you're committed to have precisely m edges in your graph. So there are several choices for that. There are n choose 2, choose m choices for that. You just think of them, you just think of this finite set as a probability space, putting equal probability to everyone. So this is the uniform model. So every graph all graphs on n vertices and m edges become equiprobable in this random model. Come to think of it, it's not so important, but so there's this GNP, which is a related model, which is easier to work with, which is the following. So you have this n vertices, and now you have n choose 2 possible edges. For each such possible edge, you flip a coin of probability p of coming heads, and every time your coin comes heads, you put the edge. So this is known as the binomial model. This GNP is kind of easier to work with, but these two models are kind of very closely related. And in fact, maybe GNM is combinatorially maybe more meaningful if you're not so much into probabilistic way of thinking. So again, when you say that a random graph GNM has such and such a property with high probability, means the following. Means that if you look at all graphs you fix your vertex set of size n, and then you consider all possible graphs with m edges, and you draw one at random, uniformly at random. And when you say that, let's say most of them are connected, that means that when you do the experiment, or if you like, a large proportion of all these possible graphs are connected. That is what it means to say that GNM has some property. In these papers they worked on, they discovered maybe two major things. One is something called the birth of the giant component. That is some kind of a phase transition that happens when m is about n over 2. There's some sudden change of structure in the graph. But then this is not, maybe I don't want to talk much about that. I want to talk about something else, which is threshold functions. So they discovered that this GNM, so several natural properties, graph properties natural properties of graphs admit threshold functions when you talk about random graphs. Let me say that more precisely. Let's consider some monotone increasing property of graphs P. A monotone increasing means the following. Means that if you have a graph that has this property, and if you add an edge, then you do not destroy the property. It's increasing. So for instance, if the property is to contain 3 mutually adjacent points, if you containing a triangle, then of course if you add an edge, you do not destroy this property. So this is a monotone increasing property. Another monotone increasing property is being connected. So you have n vertices, and if you have this connected structure, if you add an edge, you're not allowed to add vertices. You have to add an edge within these n vertices. Then you will not destroy the fact that the graph is connected. Okay, so that is a monotone increasing property. Now, if I have a monotone increasing property, then it makes sense to define this thing, so this m star n, a threshold function, so it's called a threshold function for P, that's how Erdős and Rényi defined. You ask whether GNM has this given monotone increasing property P. So you can ask what the probability is that this graph has this property, and then you send n to infinity. You ask what the limiting probability is. Okay, now this limiting probability, so remember that we're talking about an increasing property. So large graphs have to have the tendency to have this property, and the empty graph, and the sparse graph do not. So it's natural that if your number of edges m is some function which is less than this m star, maybe, yeah, so you say that m star is a threshold function. If you are below this m star, this limiting probability is 0. And you also require that if you go above m star, this limiting probability should be 1. Okay, so it's some kind of cut point. This m star is some cut point. Below it, your random graphs tend not to have the property, and above it, your random graph has to have this property with probability approaching 1. Okay, it's not, what was very interesting for them is that many properties, or natural properties that was studied in graph theory admit such threshold functions. So for instance, containing a triangle is very easy to show, so they proved that the threshold is, you can take as threshold m star just the function n, containing 4 mutually adjacent points containing k4 is n to the 4/3. So they could do this for several classes of graphs. When you kind of suddenly start to have this graph with high probability, they could also study the property, for instance, of being connected. So when is G and M likely to be connected? And the answer is around n log n. So if you're below n log n asymptotically, then you are disconnected. If you're above n log n asymptotically, then you are connected. Actually, they prove something much, much more precise than what I just said, but this is just to illustrate the notion of a threshold function. So it was very interesting that natural properties admit such threshold functions. So there is some point where suddenly, kind of below this, you don't have the property, and above it, you have. And this is sharply marked. This was one of the discoveries, very interesting discoveries in these very early papers of random graphs, first papers of random graphs. Now, actually, it turns out that the existence of thresholds for such properties can be proved easily. So it's actually a theorem of Bolobash and Thomason. They realized that there is a very general theorem that says that every non-trivial monotone increasing property has a threshold function. So I didn't say exactly what is non-trivial, but let's forget that. Okay, so from random, so we just covered this. And now I would like to go into the main part of the talk. This was quite a long introduction, but now I would like to talk about these probabilistic versions of extremal results. So in a certain sense, we'll take the results we discussed in the first 3 items of the preliminary and kind of try to mix with random graphs. Okay? So let's recall that Mantel's theorem says that the density threshold for triangles is 1/2, right? If you have a graph on density 51%, then you must have a triangle. Now, maybe I will use this arrow notation. This means the following. So G arrows half eta K3 means any fraction of edges of G, which is at least half plus eta. So any half plus eta fraction of the edges of G contains K3. So we could call this the eta Mantel property. And Mantel's theorem just says that for any eta, or the fact that the density threshold for triangles is 1/2, you can state it in the following way. For any eta, if you talk about a large enough complete graph, then you have this arrow relation is true. Okay, so this is a property. It's not quite an increasing property, but it's at least stochastically increasing. So it makes sense to ask what the threshold function, what is the Erdős-Rényi threshold of this property? So in other words, to be more precise, what is the m that you put here so that this arrow relation becomes likely? How big m has to be for this relation to become likely? If you put m equals n choose 2, you would have exactly this statement. So it's true at the top, it's false at the bottom because you have no triangles. So it will be true at some point, and you want to know when this becomes true. So this is the question. What is the Erdős-Rényi? So what is the point in which this becomes true? What is the function m that you can put here for this property to be likely? Okay, and this problem was actually solved in 86 by Frankel and Rödl. This threshold is n to the 3/2. And actually it doesn't matter if you have any fixed eta, is n to the 3/2 will suffice. Okay, actually, so I hope that given the context, given the kind of history of the area, asking for this Erdős-Rényi threshold for this property, it's a more complicated property than connectedness or containing K3, but it makes sense to ask what this threshold is, and I think it's a natural problem given past history. But actually, Frankel and Rödl didn't kind of think up this problem. They wanted to solve a problem posed by Erdős and Neshetril. So Erdős and Neshetril in 83 asked the following: given some fixed eta, very small, are there K4-free graphs that have this Mantel property? And the answer is yes. So, yeah, perhaps I should spend at least a little time to explain this problem. So this Mantel property says if you have 51% of the edges of your graph, then you have a triangle. This is some kind of, this kind of reveals abundance of triangles in the given graph. So when you say that a graph has this P-Mantel property, you're kind of saying that it has lots of triangles and they are kind of everywhere. And the question, so this Erdős-Neshetril question makes sense because you kind of say, well, okay, if you forbid K4, you are not allowing triangles to cluster much. So you want the triangles to be sparse. Can you still have the Mantel property? And the answer is yes. And this follows from this threshold determined by Frankel and Rödl. In fact, it's not only there are such graphs, but you can build many of them. If you take a random graph on endpoints and C times n to the 3/2 edges, where C is some constant that depends on eta, and you perturb it a little bit, actually you just remove some edges so that you don't have K4s, then you will have such a graph that whose existence Erdős and Neshetril asked. Okay, so determining thresholds for such properties are, I think, natural problems, but they also have applications, and that is kind of the point I wanted to make here in this slide. Now, this was only about triangles. How about more general things? Well, okay, so we have seen that, roughly speaking, Mantel's theorem, which is about triangles, Turan's theorem, which is about large complete graphs, or arbitrary complete graphs, kind of Mantel is contained in Turan, and Turan is contained in this general theorem of Erdős, Stone, and Szymonovitch, which determines, it's here, which determines the density threshold for arbitrary graphs F, and it was this quantity, 1 minus 1 over chromatic number minus 1, right? Okay, so we have this general theorem, Erdős, Stone, and Szymonovitch, which can be stated also this way in this arrow notation. So the question is, a natural question is to determine the Erdős-Rényi threshold for this. So in other words, what is the smallest m that you can put here if you want this relation here to be likely? Okay, this relation means if you take slightly more than pi of f edges of this guy, G and M, then you must generate f. So that's the question. That's the question, right? Now, this is a natural, I have been trying to convey, this is a natural problem, and several people worked on it. So it's a long list of names. And, so it was possible to establish this, to find the right theorem for some particular kinds of graphs, so for cycles of any length, and small complete graphs. So this was more or less what was possible to do, so this started in the mid-90s. And it's a little bit frustrating because you have only very specific graphs. Now, if you want to talk about general graphs, one could prove thresholds, but not one could prove upper bounds for the Erdős-Rényi threshold, but they were not sharp. They were not the right theorem, so they were weaker than what the truth should be. Okay, these methods were all basically they were based on Semirege's regularity lemma, but adapted to this context. So to some of you, it may sound more familiar to say that this Semirege method, is kind of the use of the structure pseudo-randomness decomposition. But anyway, this was only partially successful. But now, a few years back, there were some very exciting developments by two different groups of people. So Schacht and Colon and Gauss were able to determine the way they were able to prove to solve this problem. They were able to find the threshold function, m star, for this property. And here in the statement, I'm saying that m star is n to the 2 minus mu2 of f, where mu2 of f is some parameter that you compute from f. I'm not defining it because it probably is not relevant now for us. So in the case of triangles, this parameter is half, so you get 3 halves here. So this established the natural conjecture in this direction. Okay, and so these are very interesting papers, so they used very different approaches. So Schacht used a much more combinatorial, he used multi-round exposure, the multi-round exposure method, but it was kind of more combinatorial. Colon and Gauss used a more analytic approach, actually kind of very different. In fact, they did something much more bold. So instead of kind of proving this theorem, they proved a general transference principle, about which I will say just a little. So they proved, they set up a way to express density theorems, density problems and density theorems in the dense world. And then in all these problems, what you want to do is to go from this dense world to some random sub-environment. And if some theorem here is on the dense world is true, some density theorem is true here on the top, they're kind of able to produce the sharpest theorem in the sparse context. So they were able to transfer dense results to sparse, to the sparse context. And as I said, so this was kind of a general framework, so they could apply it to many things. So let's apply it to the perhaps most famous theorem in density theorem. So they were able to prove a probabilistic version of Semirege's theorem. So here the setup is the following. So I have brackets n, which is the initial segment of the integers 1 up to n, and there's some parameter m here, subscript. That means, so this notation here, by this I mean you just select m points at random from this brackets n. So it's a random m element subset of brackets n, chosen uniformly at random from all possibilities, from all these possibilities. Okay, and the probabilistic version of Semirege's theorem is this. You can fix any k, you're after k-term arithmetic progressions. Okay, you can fix any k, and you can fix any eta. Then the Erdős-Rényi threshold for this arrow relation is this quantity. So in this case, I'm telling you precisely what the threshold is. So they were able to find the threshold function for this rather complicated property. Okay, and in fact, so going after such thing was around, so the case of k equals 3 had been done earlier in 96. Very good. So let me now comment on the following. Yes, let me now comment on the following. So the early approaches these determining threshold functions for these combinatorial results, density results, were based on trying to generalize Semerity's method to some sparse context. And this was kind of limited, so it was not possible to do much. And then Schacht and Colon and Gauss kind of bypassed this regularity method, so they invented a different method to solve these problems. But still, whether the regularity method can be fully generalized to the sparse random context remained. And very recently, again it's very exciting that 3 different groups of people, or maybe 2 plus 1 somehow, they were able to prove the missing kind of bits, so they were able to develop the regularity method in full so that it can be applied in this random or even pseudo-random context sparse. And so the names of the people involved are here, so these are 3 manuscripts, all available on archive. Anyway, this is some very recent development. So in kind of one could say that this regularity method, which is very powerful in the dense context, has been successfully generalized to this sparse context, random and even pseudo-random. Okay, so maybe this was the main kind of recent development, but now I want to talk about a particular degenerate problem. I will mostly talk about Sidon sets, but so let's talk about this degenerate thing. So the Erdős-Rényi threshold has been established for several classes of density problems. So this is what the authors have been able to do. But now let's remember that for the degenerate case, investigating this function in more detail may be useful, may be interesting. So this is what I kind of mentioned before, right? So this saying that this extremal function is little o n squared is good, but of course saying this is much better. So that's the problem now that I want to address. And I want to address this in some specific instance. So here's another paper by Erdős and Turan, now from 1941. This is about Sidon set. So it's on a problem of Sidon in additive number theory and some related problems. Again, so they are interested in sequences of integers A1, A2, and so on. And the hypothesis is that the sums AI plus AJ are all different. So previously we had the multiplicative Sidon sets, right? And then we had the primes and so on. But now also this is the additive version. So you have the integers, your sequence, A1, A2, and so on. And you take all possible pairwise sums. Even you can do AI plus AI also. And you want all of them to be different. And the question is how dense such a sequence can be. Let me say it here because it's hard to read and so on. So you have S in the first n integers, and you call it Sidon if you do not have any non-trivial solution to this. So all pairwise sums are different. Now, so how big can such a Sidon set be? And the answer is, so this is some clumsy notation, but it follows the previous kind of way of doing. So this is the object, the structure that you forbid. If you forbid this, how many points, how many elements from brackets n can you have? Answer is root n. This is actually a degenerate problem, right? Root n is kind of little o of n, so it's a degenerate problem. So let me say this, again use this arrow notation. Let me write A arrows eta this, if any eta fraction of A forces some non-trivial solution to this equation. And so you can ask what the Erdős-Rényi threshold for this Sidon property is, and you can read out from the results of Schacht and Colon and Gauss that the threshold is n to the 1/3. So so again, we consider this random subset, m element subset of n. What is the threshold for the Sidon property? Well, it's this. To say it more explicitly, maybe this is the kind of easiest place to read. So if you're interested in when this extremal function is little of m, let's remember that brackets nm is a random m element subset of brackets n, so it always has m elements. And the question here, this extremal function asks of this m element set, if I take out, if I want to find inside it a set which has no non-trivial solution to this, how big can such a set be? Well, I want to know when the answer is little of m. And the Erdős-Rényi threshold for this is this quantity n to the 1/3. So m is n to the 1/3. So if m is a little bit bigger than n to the 1/3, then this statement is true with high probability, and if m is a little bit less than n to the 1/3, this statement is false. This extremal function is actually close to m. It's asymptotic to 1 times m. Okay, so this is what you can read out from these general transference theorems by Schatten, Coulomb, and Gauss. But now we want to pinpoint this function for the whole range of m. So again, I'm kind of trying to stress that we are kind of trying to do this instead of that, right? To find some explicit function. And the theorem is as follows. Let's talk about m, which is of the form, let's say m is n to the a, right? It's some polynomial in a, and a is some number between 0 and 1. Then the theorem is that there is some constant b, such that this extremal function is n to the b. Let's not say much if I don't tell you what b is. And b is this. B is some piecewise linear function. Actually, let me say this in a picture. It's like this. So yeah, here I wrote, so it's f because f is simpler than x of n and so on. So the largest Sidon subset that this random set can contain has size n to the b, and b behaves as a function of a like this piecewise linear function. So as a grows from 0 to 1/3, b is the same, b is equal to a. Now at 1/3, you would expect something different to happen because of these previous theorems, but then for some reason it's kind of flat like this. So in other words, if you take a random subset of brackets n of size, let's say n to the half, so here at this point, the size of the largest Sidon subset of this random set has size n to the 1/3. And if you vary 1/2 between 1/3 and 2/3, this doesn't change. Actually, it's even known that it's n times log n cube root n, cube root of n times log n. And then suddenly at 2/3, this behavior changes, and it kind of grows like that. As you increase a, this extremal function increases linearly. I mean, the exponent grows linearly. Now, I should probably stop. I just will say that, so this was the case of the equation x plus y equals z plus w, so Sidon. But there are natural generalizations. There are things called B3 subsets. So then, well, this is the equation. So 3 terms, the 3 y sums, all different. And one is able to prove similar results. And let me just show you the graph that you get. So one is able to prove a lower bound and an upper bound. So there is some unknown, some region here which we cannot completely pinpoint, but actually we believe that we can prove that this lower bound is the same. So again, we have this graph kind of growing linearly and then completely flat and then growing linearly again. So this behavior of this degenerate problem seems interesting and somewhat surprising. It's not clear why this degenerate problem has this kind of flat behavior in the middle, and then suddenly kind of it changes its mind and kind of does this. Right. So thank you very much.
Are there questions?
So when the density threshold is 0 for
Right.
problems, you say that this theorem about the threshold density for the problem. When the threshold is 0, there is always an exponent smaller than 2.
Yes, it's conjectured that there is an exponent. It's actually the function is asymptotic to c times n to the alpha and rational alpha.
Yes, but it's proven that it's smaller than n to the 2 minus epsilon for some.
Yes, right. Yes.
Any other questions? So let's thank the speaker again.
Thank you very much for listening. Thank you.